Hello everybody. Let's look at this problem with the block. I'm going to make it large here so we can look at one thing at a time. So let's see what is going on. Please read it carefully. Notice everything that is given. And the question is, what is the minimum speed of the block at D? Here, what is the speed here at D? So in order to make it and to be part, wait, it's not writing, okay. Okay, this is part of a circle. So right here, the free body diagram, the forces acting on the block is mg and potentially normal force. In order to make the circle, it needs that the sum of the forces to be equal ma centripetal. So it has to have enough velocity to provide that. At the minimum speed, we are going to assume n equal to 0, the normal equal to 0. So for any speed greater than n, so that way we solve for minimum speed. So when n equal to 0, instead of sum of the forces, we have mg. And we know the centripetal acceleration is v squared over r. And remember, this is v mean. Any v greater than that will provide some n. Okay? So we can see that mass cancels out, doesn't matter. So v mean, that is v at d, equals square root of r times g. Now r is given, for me is this value, g is, sorry, I wrote r times r times g. G is 9.8, so plug your values and solve for d. So that is part A. For part B, it's asking what is the minimum kinetic energy for the block at point C, so kinetic energy at C, in order to make it to D. So let's see what happens between C and D. Between C and D there is no friction, so energy is conserved. And let's see what else happens. So we are going to measure everything relative to C, so no potential energy at C. So at C, so between C and D, total energy is conserved, energy at C equal energy at D. At C has only kinetic energy, and at D has kinetic energy at D, 1/2 mvd squared that we just calculated the D for it, plus mgh. And h at D is above the ground 2r. So we are going to put here 2r. mg2r. So here you go, you plug your numbers and calculate for kinetic energy at C. The next part is asking what's the minimum kinetic energy at B in order to make it. So we go one step further at B. Now between B and C there is friction, so something happened between B and C. Some energy that has at B gets used as work done by friction. So this is about work kinetic energy theorem. Work equal change in kinetic energy. So work done by friction, that the force of friction is mu n times the distance, that's going to be negative, is change, is kinetic energy at C, that we already calculated, minus kinetic energy at B. So from here, you can solve for kinetic energy at B because we know kinetic energy at C. And the normal force here, between B and C, there are two forces acting on it, mg and n. And the object goes to the right. So n must equal mg for this portion. So n is mg, that's negative. Make sure that you write it well and solve for kinetic energy at B. Now the last part of it says, what is the minimum height from which the block should start in order to have, okay, let's get rid of this height, okay. in order to have enough speed at point D, so the block will not leave the track. So actually moving further, right? We found the kinetic energy at D, at C, at B. Now how much, let's read again. What's the minimum height in order to have this kinetic energy at B that we just calculated? So what happens now between A and B? A and B, no friction. It says it starts from rest. So kinetic energy at A is 0, but has potential energy, and it's asking us about this height. So between A and B, again we have conservation of energy. Energy at A equal energy at B. Energy at A is only mgh, and energy at B is kinetic energy at B. That we just calculated the previous part. So from here you solve for h. Okay, good luck.